All right, today we have Dr. Nina Stark. She is coming from Virginia Tech University. She has a very interesting sort of varied background. I'll read through quick. She got her MS in geophysics in 2007 from the University of Münster, Germany, where she was working with the German Naval Research Institute for Underwater Acoustics and Geophysics on mine burial prediction. She then went on and did her PhD in 2011. She finished up in In-situ Geotechnical Investigation of Sediment Remobilization processes at Marin Center for Marine and Environmental Sciences at the University of Bremen, Germany. She then made her way over to Canada, where she worked at Dalhousie during a postdoc, and she sort of introduced herself to the world of coastal processes and physical oceanography. During that postdoc, she decided to go take on become a professor, and she's been doing that ever since. And she's going to, I think, give us sort of a synopsis of some of the different projects she's been a part of. Last year in 2018, she was awarded the NSF Career Award, which is very impressive for the early stage of career. She's accomplished a lot. It's very fascinating.
Great. Thank you, Josh, for the kind introduction. And good afternoon. I'm really excited to be here again. I enjoyed my stay just as much as my previous days. I really love to come up here. And so I think last time when I presented to you, I was talking about an Arctic expedition that we did. So today I will give a little bit more of an overview of different projects we are currently pursuing. So the title is actually in line with probably what is the title towards most of my research. So in situ, we are a really hardcore field work group, right? 80% of our work is in the field. We are doing lab testing, but we are not very innovative on it. We are more using that for ground truthing. And when it comes to numerical methods, we are usually trying to find collaborators to work with us because our strength is really in the field. We're looking at geotechnical investigations, so that's really the perspective we are looking from. We are looking at soil mechanics, and then with a focus on coastal sediments, and we are interested in sediment remobilization processes. That means we're interested in erosion, transport, deposition, as well as sediment stability. So for different applications, and I will come to one of those in a second, we are also interested in not just transport processes, but also general stability. So usually I'm not a big fan of outlines, but for these longer talks, just that you know what you can expect. And in case you don't like this, you can run out right now instead of wasting the next hour of your life with me. So I will talk a little bit first about motivations. I will talk a bit about methods, because that's a big part. We are encountering a lot that we would like to measure things, but we cannot measure them because we don't really have tools for it. And then we are in the really exciting business of then trying to develop tools for this. So I will talk a bit about instruments we developed as well as instruments we're misusing for other things. And then I will come to 3 really brief examples out of 3 studies here before ending up with some concluding remarks. So motivations. So one topic we are currently looking into is beach trafficability. And so I found this photo, I think this is from Australia, and it has the title, "The Beach That Eats Cars." Right, so this is not only a problem in Australia, but recreationally you can find that people get stuck. That's fairly unpleasant, but perhaps not much worse than that you have to pay a tow truck to pull you out again, right? Not great, but not that bad either. But it is actually a big problem for the Navy, particularly for landing missions. And it is also a big problem if you think about evacuation. In 2017, I had the opportunity to lead a team of geotechnical engineers into the Hurricane Harvey area. We arrived 2 days after landfall, and we visited Mustang Island, what is a barrier island down there in Texas. And there were electricity poles all over the one highway, so everyone was taking the beach to practically move around and get off the island. So if you get someone stuck there, and then the water is coming closer, or you're just blocking off that route, that's actually becoming a really big problem. As Josh mentioned, so I started out actually on mine burial problems, and so I had the chance in the Sylt project to follow up with that. So here we are interested in unexploded ordnance site characterization and monitoring. So we are looking into, from the perspective of currently you want to use remote techniques to actually do monitoring and site characterization, in particular if you would suspect that there potentially are munitions. But so a lot of these techniques that scan into the seabed will need some information about the seabed. So currently that often means that you look at it and you see sand, and that means you're actually calibrating your methods for sand. But that doesn't really work well if you have a lot of changes in porosity, what would change your results in acoustics, for example, as well as in EMI. And it would also be quite of an impact if you would just have a thin sand layer on top of clays, what in a lot of environments can actually be the case. And so then this is actually the project that I got the career award for. So we are really looking into hoping to bring more geotech into sediment transport expressions, in particular with a perspective towards sea level rise and extreme events. So if you just think about it, this like kind of really busy graph, but I guide you through it. So if you have the immobile bed, and this is kind of how I see the world, right? So you have the water column, and then on top you have sediment, and you have grain size distributions, but you also have density, you have a shear strength, you have a porosity, and you have pore pressure responses and friction angles, right? So more geomechanical properties I'm interested in. And you have a certain state that it is in right now. So now if you switch on practically the laundry machine, right, and you put some stresses onto the seabed and you start moving sediments, either as suspended or as bad load, and you may be forming actually some bad forms here, what does that actually do to these properties here, right? Probably you're mixing up things, you get a different density, you have a different porosity, means you're changing your friction angle. But then, hey, let's wait, the friction angle should also actually affect how easy you can mobilize sediments, right? So you're coming into this circle of you're changing these properties that are also input properties. And so it's getting pretty complex. And the biggest problem is that we don't even get good measurements of in situ friction angles yet. So we struggle with really getting values for that, to putting that into the system. You might find expressions where, for example, to stay with the friction angles, you use friction angles to get an idea of how erodible the sediment is here. But very often in most studies, if you look into what kind of friction angles are used, you will find it's either 32 or 33 degrees by default for all sands, or you just find textbook values. But to actually get a feel for how it in situ is with different densities is very hard. So then if we go even further, so if you think about the nearshore zone, this is already complex, right? But so these sediments get more adapted to the conditions they're experiencing. What if you now inundate an area that is not exposed to these shear stresses, right? So you may have finer sediments there because they have not been washed away previously. So now you're exposing them to currents, to waves, so they should actually erode much quicker. So currently we often assume that our erosion prediction, what we learned from the nearshore, is being applied for also inundated areas, but just theoretically, you could state the hypothesis, you may underestimate how bad it may get in inundated areas, right? So this is something like a bigger picture where we're trying to follow up, really bringing more geotech into sediment transport, and then also looking into the future, particularly for sea level rise in inundation areas. Okay, so some of the methods we are using. So I mentioned we do mostly field measurements. We have actually the biggest academic geotech lab in the US at Virginia Tech, what is a great resource. So for the calibration, we can go there and conduct almost all tests. I think in the US, it's only Fugu who has a larger lab, and that's a commercial company. So we can practically run most tests, geotech tests you can dream of. But as I mentioned, we work mostly in the field. So these are our prime field methods. So this is a portable freefall penetrometer. It looks like a little torpedo. It falls through the water column, it impacts into the seabed, and it measures its own resistance and ambient pressure. Its own resistance that it experiences from the sediment depends on shear strength, depends on friction angle, depends on soil mechanical properties. So we are using this very simple tool to get not so simple parameters. So deployment is really quick and easy, data processing not that easy, so that's actually something we are still heavily working on, in particular going further towards, for example, getting a porosity value out of the measurement directly. But the attractive part is that you can drop this device actually through waves, and you can get get a feel for how hard or stiff or soft the seabed is right in that moment, right under these hydrodynamic forces, right there on your sandbar, for example, right? And so that's why we wanted this little device that can be easily deployed in challenging and energetic environments. So then we're also misusing pressure transducers. So these are actually just standard wave gauges you can buy off the shelf. So what we do with them, we not always strap them to rocks. We also mostly put them into a little nicer configuration of like a vertical array. But so in that case, this was in the Arctic, and this was the only anchor I could find as a rock to put it on. So what we are doing with these, so we put a geotextile on top so that we cannot have the sediment actually push against the pressure transducer, and just let the water in, and we place them in beaches. And we are interested in measuring how the pore water pressure feels like under wave action. So the motivation behind that is mostly associated to liquefaction processes. We know that in ocean environments, we can create liquefaction through buildup of pore pressure. That's a similar process that we're knowing from earthquake engineering. We can get it from vertical pressure gradients. We can get it from horizontal pressure gradients. And so we are really interested in measuring that in the field, because there's still very, very few field data sets, and we've learned in particular in coastal environments, a lot of what we see in offshore engineering on liquefaction and oil rigs does not really match what we are seeing here. So this is something that we have gotten into more recently, motivated by the beach trafficability problem, and that's using remote sensing, in most cases here based on satellite imagery. So we're using multispectral images, so optic images that's practically, in this case, using worldview, means RGB and the near-infrared band. And we're using SAR, usually either Cosmos SkyMate satellite or TerraSAR X. And we get actually images with a really small pixel size. So it allows us that we get multiple pixels even at narrow beaches, so that we can really look at different zones of topography or like moisture contents, for example. And we'll talk a little bit more about that later. So let's look at one of the projects I briefly want to present. So this is actually something that one of my PhD students, or former PhD students, I should say, he graduated last year, really got excited about when he was working with Jesse McNinch and Heidi Wattman out at Dept. And so having the pier there, we thought, okay, this would be a great opportunity to actually measure with a penetrometer how the seabed feels under different wave conditions, because it allows us access to a very energetic environment while also being safe enough to do this, actually. So this is just a strip on the pier. I'm sure most people here are very familiar with this facility. So we found these different locations, and we stayed there and went back and dropped the penetrometer along these locations. Again, the motivation here was to investigate a correlation between in-situ geotechnical properties and hydrodynamic forcing in the nearshore zone. And more simple, I guess, the goals that we directly really were hoping for is that we get these measurements of the sandy seabed under different wave conditions. And then we had also cooked up an idea if we could come up with a coefficient that would tell you if you have certain wave conditions and this water depth, how much softening of a sandy seabed would you have to expect, right? So in particular for like, civil engineers in coastal environments, that would be very attractive. And we think that there's this relationship, so we started cooking up a factor and wanted to try this out. So these were the days that we were measuring. So we had a couple of days of fairly moderate or calm waves, and then we actually had a storm event coming by, and I have to give big credit to Heidi Wattman, who was brave enough to go out on the pier during these conditions and drop the penetrometer despite the waves. And so this is what we are getting. So up there you see what we call the CWS, sorry, not very creative, stands for coefficient of wave impact on the seabed. So we are engineers, we're not too creative, I guess, with these things. And so what it does is on the bottom, you have water depth and your wavelength, kind of with the idea of thinking about depth of closure, something like that, right? And what we are actually inputting from the penetrometer is the following. So you see here, This is what you get from the penetrometer measurement. In fact, you get the deceleration, you do one single integration over time, you get the velocity, and you do the double, and you get your penetration depth, right? So this is practically straight up measurement with not too much error option in there. You actually see two deployments here. So you see one in blue and one in black. And you may say, well, they're overlying really nicely up to here, but they're completely independent. You pull the penetrometer up and you drop it again. So, so you have actually quite some reliability. And then you may say in this kind of greenish area, well, I don't even see anything there, something happening. But so that's why we have the zoom here. So you see that you have much less deceleration. What does that mean? So the penetrometer impacts the deceleration measures how much it slows down. So it means in these top, in this case, 8 centimeters, the penetrometer almost did not slow down when it actually felt the sand. Well, then when you went past 8 centimeters, it suddenly slowed down very quickly, in fact, so much that it stopped, right? So it means what we in fact have is kind of a really like very little resistance layer over a much harder resistance layer. You think about duck, in this case, this is one location, not too far out, not too many finds out there yet in the samples that we found. So what you're actually having is a loose layer of sand that was nice and stirred up over the more compacted, stable substratum, right? So if you think back about the factors, so what we are relating here is on the one hand, in Z, this is the thicknesses, this is how thick this top layer is, versus your overall penetration depth, and then how much of deceleration you are reaching here, versus how much deceleration you reach in the maximum here, right? So it gives you kind of a relationship, how soft is the top layer versus how hard is the substratum, and how thick is this top layer versus how quick are you stopping. So what we traditionally do with these deceleration measurements is a calculation that we call the quasi-static bearing capacity. So in a nutshell, that means we take the deceleration and make a resistance force out of it by just using Newton's law, not much magic in there, right? The penetrometer is tapered, we don't have much side friction, so most of the resistance will go against the nose. It's also really smooth, so we don't have too much on that, and it's also like really drag reducing in shape, so we made the calculations and impacts of drag and friction are really low, so the biggest resistance is literally the tip bearing resistance against the nose, right? So that is good for us because that's what geotechnical engineers can work with best in this case. So that means we get the force, and from the force we consider the area of loading from our geometry, and then we get practically the load or the bearing capacity. That leaves us with the fact that our penetrometer is slowing down, right, from about, in this case, 5 meters per second to a stop, and we know that soils are actually strain rate dependent. Imagine you have a clay and you try to hit it really hard, it may hurt your fist and it feels much harder. But if you poke it really slow, then clay is really soft. This is strain rate behavior. So your strength actually depends on how quickly you're straining the soil. And the same happens to the penetrometer. So we have to correct for that to account for different velocities, and that's what we call the strain rate correction. And what we get out is a so-called quasi-static bearing capacity. You need an empirical factor for that. We don't really like that because it's also a soil-dependent factor. And that is also the reason why we are often stopping here and not make the next step towards a shear strength, where we would need another factor, often called the cone factor, would be a second empirical factor. But you could relate this practically directly and linearly to an undrained shear strength. So we have these big error bars. That's actually the uncertainty that comes from the variability of our empirical factor. So instead of saying, oh, we think it's that, we're just saying our true results is somewhere in there. So going back to our coefficient of wave impact, so these are the results from the different days. And so in all cases, you see a bit of a development that this factor is getting higher. We don't really like that the factor overall is very small, but so we're still working on this. It's still work in progress, really. But so what I want to point out, so you have really a shallow zone where this factor goes up very strongly, where you have a lot of interaction with the bed. Then you have an intermediate zone, and then you have a zone where the factor stays really low and there's very little interaction. And in fact, that is matching fairly well this condition, in particular from intermediate to deep, with where you would also expect a depth kilometer. So we can actually feel how the waves are changing the seabed conditions here. And we are really excited about this. Again, work in progress. The CWS is certainly not perfect yet, but so we're trying to really get more into depth here with the idea of what if you tell me these are the wave conditions, and I can tell you how much the seabed will soften up and how deep. And that would also mean, if you think about sediment transport, that this softer, this looser layer is much more available for sediment transport. So this is here the strength values. If you plot them like that, and as you expect, where there's a lot of interaction going on, you have much more variability here. And most specifically here, you have this really strong drop here, what is usually either related to that you have deposition here. That could be, for example, your trough. You know, if you have the sandbar and the sandbar is migrating and just dropping fresh sediment there, that's usually very loose. Or you could have that you're just stirring up the surface here. But you see also really strong differences here between the non-storm days and the storm days. And if you just look at the magnitudes, I know it's a really busy and a little bit chaotic plot, but so that means during the storms, you're actually softening up. And this is the maximum strength. This is not the top layer. You're practically softening up the whole seabed in that region significantly more versus in the non-storm conditions. So this is just like putting it back together a bit more, like averaging over these different profiles and the multiple drops here. And you can see here again how you have here really the interaction with the bed really soft. And the other thing you can see that it's tapering off, so you have a little bit of softening with a distance, right, where you have deeper water. So here you have actually two effects. So in the shallow water, you have really the waves that are controlling the hardness or softness of the seabed. If you go further offshore, it's actually refining in the sediment distribution that makes it softer here. So just in summing up some conclusions, and if you're interested, this was published in Coastal Engineering. And again, we're still working on this, but so the two main things were really that we were actually able to put some numbers to how much the seabed is softening up with the waves. And I agree, we all expect that, but to actually put really numbers to it, that was really our big goal. And the other thing is that then if you go more to the distance, you also see the effects of the sediment fining here, right? We also saw that during the storm, you're really like dropping the strength overall, not only in the top layer. And as the storm continued, it actually got harder again. And that's something we have seen in other places before. So you're stirring up the bed, and then you start moving around to stir it up stuff, and what you're leaving behind is much more stronger surface. We have seen that in particular in a project where we looked at bar migration in New Zealand, where we could see where the bar is going, because that was really soft, that is where the sediment was deposited, while where it was freshly eroded, we saw these really hard surfaces. And then the CWS factor reflected both the wave breaking, I didn't point that out here so much, as well as the depth of closure. And so we are working on refining that in hope that perhaps we can develop it further to a factor that may be of interest to the coastal community, as well as the more construction side of coastal. Okay, let me move into the next very different topic. So here we are not using the penetrometer, so I'm going through these different methods here. So here we're going through the pressure transducers. So the idea is this is kind of based on a graph that Diane Horn had published before, a little bit altered, and here we put our pile in and we have different pressure transducers. And so we have done that at different locations, but today I want to talk about a location in Germany. We went to the island of Sylt, and this was in collaboration with the Technical University of Darmstadt, with Peter Mevis, who's mostly a modeler, and he's interested in the behavior at Sylt. And we were interested in pore pressures on the tidal and wave forcing in the intertidal zone, and how that changes in crustal variations, the sediment strength. So Sylt is this really narrow strip here. As you can see, it stands a little bit inland. And there's a fun fact, I mentioned it just to Josh. So Remoer, the next island, is actually Danish. And so Sylt is the beach, and Westerland is eroding extensively, and all the sediment is going to Denmark. And that has become a big political problem, because the Danish say, that the sand is Danish because it wants to move to Denmark, while the Germans say it's German because it's living in Germany so far and should pay the taxes, right? So it has been it has been quite a bit of a long drama there, and it's still ongoing because it's eroding so badly. So we were kind of in the middle of the island, and this is the strip in Google Earth that we worked on. This is a photo of how it looked like. So we had pressure transducer arrays in 2 locations, and we buried then a whole rope up to the dunes, so in case we would lose them, that we would have them still hanging on the rope. And we also used our penetrometer here, actually for the first time, to dropping through air, because we were interested in how actually at different days here the intertidal zone feels like. But let's stick with the pressure transducer. So up there, this is kind of what you get out of the sensors. Keep in mind we're in the intertidal zones. We're actually going through some draining phase there where we're running dry. In between, you have obviously the tidal cycle and the waves on top of that. If you clean up a little bit by averaging, you get the waves out and you just get your tidal cycles. You can also check on if actually your pressure transducers were in the alignment that you were hoping to place them in, but it's not always that easy with these long ones from the distance that you're seeing here in the water head. But so what is really most interesting about this data set is actually what is happening when the water is drawing down, when you go into low tide and the location was actually exposed. So you don't feel the waves anymore because your water is actually past your location, and you're seeing, so these are 3 different sensors. You're going from blue is actually the one that is the highest up, right? It was right under the 10 centimeters under the beach surface. And then you're going 10 centimeters further down into the ground. So purple here is the lowest one where you have still groundwater, and you see that the groundwater is actually draining out of the beach. And if you measure like dimensions and you take hydraulic conductivity of the beach, this gradient actually matches really well, that the water is taking the shortest way out of the sediment, and that works very well. And you see that the 3 deeper sensors all show the same thing. But the top sensor, wouldn't you expect that that's going dry? So we were really confused about what's going on here, so that this should actually be dry here, but the top sensor says there's about 10 centimeters of water on top, while the sensor, the next one down, says it doesn't feel any water anymore. So that was very confusing for us, because even if we were not sure this was actually a light measurement, it could have been that there's no water there, but then why would this sensor not see the water? So what we did, we tested the sensors up and down, because I told the students the sensors are broken. Right? Something must be wrong there, and particularly on the low measurements, and then they came back and said, no, the sensors are good. Something is going on here. So we came up with this following hypothesis, because what we observed is that at this pillar that we had, that there was actually a little puddle, right? So we had, in fact, a little bit scour, and there was a little puddle, and the 10 centimeters matched really well. And these little waves you saw were actually still single run-up, like of some gravity waves that occasionally made it up there because we were actually not that far away. So that made all sense. But then the question was still, what's happening with our next sensor here? Why is that running dry? Because you would think that it can still see the top here. So the only real hypothesis we came up with, and this is still a hypothesis, I was unfortunately until now still unable to get a similar data set to that, is that you actually have, despite the fact that there's a puddle here, you have a lot of air intrusion and in this layer underneath. And the air would actually be a good like ice insulation so that you would not feel your 10 centimeters here. So now you may say, yeah, who cares, right? If there's a little bit air and 10 centimeters of sediment, it actually matters quite a bit. So what does that mean really for your run-up? Could this, if you think about like how soil mechanics with different phases work, right? If you have water and if you have air in the pores, you're actually creating suction, right? So there's in geotechnical engineering, there's a whole field that is expanding rapidly on so-called partial saturation. So where you're not fully saturated, but you're also not fully dry, and you're actually creating what is called an apparent cohesion. So a cohesion that is not due to cohesive sediments, but due to partial saturation that strengthens your soil, right? So if that's the case, that means you suddenly have a stiff layer that is just created by the right amount of moisture and air right here, that may also mean that runoff is being directed very likely above this layer, right, and would not sink in right away. So this was really an interesting finding. We're continuing the measurements and we're actually trying to still fit places where we have the right gradient and places in the right spot to create a similar system. So here again, we came up with this first conclusion that maybe the partial saturated layer works as an insulation here and redirect surface water. And we investigated, I don't present that here, also pore pressure response to wave action. And then we did do a correlation to the penetrometer results and also found really interesting findings on that. We're currently still working on publishing that, but so stay tuned for this. Okay, quickly the third one, and here we're going to remote sensing. So the overarching goal, this is actually a collaboration, again, with Jesse and Heidi from the Army Corps. Then Hans Graber from CSAS at the University of Miami is helping us with the satellite images. We are looking forward to come here next summer to work with Tom more on this project on the remote sensing. So the idea is here we want to correlate geotechnical parameters and soil behavior to remotely sense properties. We are pretty open to different remote sensing data. We're also acknowledging that we probably cannot get one image and all information, but we are more thinking about what if you have different sensors and we're merging all the data. But in an ideal world, we would like to have practically a data analysis framework that we can pull in, for example, different satellite images, and then do a rapid assessment of coastline sediment strength, stability, and trafficability. That could be, again, like if you think about the naval missions, emergency applications, but it could even go to something like a slope instability and have the accessible sites. Okay, so the more direct objectives is to just correlate geotechnical soil characteristics with multispectral images and SAR backscatter. We want to go for what does moisture content do, liquid as well as frozen. What are the optimal settings for sensors, data fusion, I just mentioned, bringing in different data as an analysis framework, and then eventually develop this framework. So this is some work that was actually a first step towards that. I don't know who's familiar with how it was determined if the Apollo is sinking to the moon or not. So actually a colleague of mine at Virginia Tech, he was involved in that, and so he used analog images and shadows of craters to determine topography with high resolution slopes. From the slopes, he came up with slope stability and then geotechnical properties, and that's how he predicted the bearing strength of the moon and how big the landing pads had to be so that the moon landers would not sink in. So when we were starting to think about beach trafficability, I asked Dr. Mitchell and I said, Jim, what do you think we do the same on the beach? And we have much better imagery and we're much closer to home than actually moon back in the place. And he looked at me a bit skeptical. I think that's his thing, right? And then he's like, well, I don't have a reason why I would not. And that was enough to really go for this. What you're seeing here is actually not satellite images. These are structure from motion from UAVs, or what we up here is actually just like what we call random people images. So you walk by a feature, you take 5 images, or perhaps you take some photo shoots with your family, and you have the same feature from different angles. And so the upper reconstruction is actually based on only 5 images. So it was not that we used hundreds of images, but just 5 images to construct this file. And then we derived the topography of these different features. Down here, these are actually footsteps. So this little wiggling here is not error or uncertainty, it's actually the footsteps in the sand. And from that, we looked at angles. The other thing we did in the same process, we took satellite images, these are aerospeed multispectral images, but you don't even need the multispectral in this. We did really simple things. So one time we just converted practically grayscale to a surface, got this big wave, understood that the wave is because the one side is illuminated by the sun, the other side is due to the shadow, so we flipped the shadow around, and then looked at the angles that we get in the percentage of the illumination of the slopes. And then we did the same thing that Jim Mitchell did for the moon. We looked at shadows of features and determined slope size based on the shadows, and we knew the sun angle, and looked then at what kind of slope angles we're looking at. So if we then put that together, we came out at this. So this is the pit with the satellite emission that had a really, really large frame, the mount much smaller, and then we had here the mount from this is the mount from the images, this is the mount from the satellite, and then we compared this to actually shear test of friction angles. So this is conducted using a tilt table, so we are practically getting an angle of repose by preparing a soil sample and start tilting it. And this is the direct shear test based on really standards published in ASTM, not anything different than in a normal consulting job you would do. And we got a fairly good agreement in this case with the mount data from the satellite as well as from the imagery. And that was quite fascinating. If you run 10 of these tests, you probably have just as much variability as we've seen here. And keep in mind, these tests would take you days, while we just got a really quick snapshot. But something we also realized, as soon as you put a little bit moisture content, even just on the tilt table, your friction angles blow up, and here we're talking partial saturation again, right? So we have a section between the particles. And the same happened with the pit. So our results in the pit were not wrong, but because the pit is just not illuminated the same way, it doesn't dry out the same way, so you actually have a few steep walls that are staying together due to moisture content. So what can we do about moisture content? So this is a SAR image, also from Dept. So here on the left side, this is the TerraSAR X image. And just in this, you can already see that you can actually see these different zones of moisture content, almost clearer than if you would just walk up at the beach. This looks like a really big transition zone. The only thing is that this is the dry versus moist area, right? So then in the SAR, you see that also reflected really well. And if we put it a little bit more into actual numbers, so this is the backscatter intensity from the SAR image, and here you have your different zones. And I agree that this is still very qualitative, and this was based on data we collected in 2016. We just put the different zones together. But so we found that there are actually different effects in the dune as being a big topographic feature should do this. And then the dry sand, the lower, we also expected if we have partial saturation changes in saturation, we would not expect a linear relationship. We would actually expect a nonlinear relationship. And then the bore really spikes out. So Julie Paprocki is a student of mine who's working more on that. And so she has currently working on new SARs. This is still multispectral imagery. So in 2016, we were not visionary enough to actually do moisture content measurements while doing the satellite images. So we have caught up with that a little bit. We started last year in Duck and then did that also in Alaska. And continuing this year again, we had just last week at a farm in Virginia an experiment where we would prepare different moisture content soil patches and then get satellite images over it. But so we now got a few data sets with actually moisture content values like measured from samples as well as a moisture content gauge. And here you see the near infrared reflectance and the red band reflectance. And you see a pretty good relationship here, and these relationships are actually in line with expressions that have been developed from agriculture, right? Where people have already looked into this aspect of determining moisture content. And so this gives us a really good confidence to go a little bit further with this. And this was one of the first data sets when we tried this. So I agree, there's very little data points on it to really confirm it. But now we have more data sets to go for this aspect. So just to also wrap up this, and keep in mind, these are really first conclusions and probably more next steps, but so we're getting more data in there, but it looks really promising that we can get geotechnical parameters from airborne and satellite imagery. We have so far focused mostly on sandy sediments. We want to spread out. We want to also get more fines in there and go to different environments as well. We need more like data to also get these correlations a little bit more set and more validated. And then we were really looking to what are also method environmental dependent limitations. So what kind of frequency bands, for example, work for a certain soil type best, right? What are impacts of potential vegetation that is in there or shelf fractures? And again, more data is needed, But again, we were really excited about the fact that there was at least trends that are promising at all, and so we are looking to explore that much more in the future. So just concluding remarks, so I showed you the results from the penetrometer in the nearshore, looking at sediment transport and how that interacts with geotechnical properties. I talked a little bit about what we are doing with remote sensing as well as with pressure measurements in the intertidal zone. And so if I would just wrap it up, I really believe that geotechnical parameters and data can contribute to the understanding of coastal processes. And I hope that we can have more collaborations, working closer together to really bring that in. But there is also this aspect that new methods are needed. A lot of the standard instrumentation and tests we have are really not well suited for coastal environments, or are practically not safe, right? Some of the more standard penetrometers, you could never deploy that in really rough waves without risking the instrument or life of the operators. And of course, there's still much more data needed. And with that, I conclude my presentation. Thank you so much, and I'm looking forward to some questions. Okay, let me just repeat. I think for the microphone, I should repeat the question. So the question was if we don't take course. We do take course. We are not too excited about taking course. That's why we usually don't present them much, because that's just not our main aspect. But yes, we do take course in Shelby tubes. If we really have to make sure we have to preserve the sample as much as possible. We so for example, for the remote sensing experiments, while we take the images, we practically have a whole group of students there who do in-situ moisture content, in-situ strength, but also take the course, mostly with Shelby tubes, really carefully. And we even push them in and dig them out instead of pulling them out. And the same for in water, and we use mostly a gravity core and sometimes a fiber core to actually get cores to calibrate and validate. So the idea is we want to have less core samples, but use them to validate, calibrate our in-situ methods.
But the information you're getting isn't, you're not actually doing composition of your sediment, but solely this composition.
So with composition, you mean mineralogy, is that right?
Yeah, like if you were to do this experiment on wine.
Right. We are interested in that. We actually are currently trying to set up an experiment in Jamaica to go on a coral sand. Our biggest issue with that is currently customs. But so there is a plan for that. The beach in Alaska that is actually on the title page is a quartz sand beach with heavy minerals. Behaves very different. So there's quite a bit of titanium and gold in there. It's not shiny, it's all black. But so we are interested in that, but we are, I guess, secondary interested in that. So we acknowledge that it has a big impact on the main primary things we are interested in. As I mentioned, the coral sand behaves completely different than the quartz sand from our perspective. And we're branching out. I showed a lot of quartz sand examples here because we're just starting to get into. But we have worked in Hawaii and compared that, for example, against quartz sand from the North Sea with a penetrometer pretty extensively. For the remote sensing, as I said, we did this heavy mineral beach in Alaska in comparison to duck, and now we're trying to get the coral sand in Jamaica. Thank you. Yes?
You ever worked in areas where you were in fauna and you worry about how that might, spatial or seasonal variabilities really make this complicated?
Yeah, so the question was if we also do measurements in fauna areas and how we consider that, is that correct? Yeah, so so we are actually in a wider range impacted by that quite a bit. So plant fibers and the penetrometer results are really easy to detect. So they work as I always say the trampoline effect. So they slow down the penetrometer and even make it even bounce back, or the penetrometer breaks through. So we have even in some single project assisted people who were thinking if there was vegetation that was, for example, berries, and found such layers. In New Orleans, we have a famous example where there was a sediment dredging project, and they were concerned that there was a lot of burial. we could see very clearly in the penetrometer that was going on. That is not so much focus, I guess, of our research so far, but we have contributed to that. With regard to other biology, we have actually, and I didn't present on that, that's actually my own project, I did not present on that here. So we have a current NSF project on the interaction of soil properties and bivalves. So in that case, the big idea is could like oyster or mussel aquaculture at some point become a scour mitigation method. But as a first step, we found very little information of what they actually do to the soil properties, to the adhesive protein they're using, for example, catching, right, as well as to when they're breaking down. And we know what shell fractures are doing, but no one has really looked at it really close to such reefs, right? So that's something we have actually a whole project on. And then in the past, the other interaction we had a lot with biogenic life was also tube worms. So tube worms really are, like for the penetrometer, quite interesting because they build these strong carpets that make really strong peaks. And we have found multiple sites in the world where we get a strong peak and the seabed surface seems pretty strong, but then the penetrometer pokes through it and it's really soft underneath. In one example, we actually had that a construction site lost 50% of their lobster houses because they assumed that the strength of the seabed surface was much more tricked by the tube worms, and it was much weaker. So as soon as they lowered the lobster houses, they broke through the carpet practically and just sank into the mud. So we have some interaction. We have one project now, and NSF is actually heavily supporting interaction between geotechnical engineering, they call it bio-inspired geotechnical engineering. So we are tapping only slightly into that, but we are affected by it a lot, acknowledging it a lot, and try to learn quite a bit from it. And I guess at the beach, another thing is also burrowing creatures and what they do with regard to the pore pressure as well.
You ever thought of turning it around a little bit and using for outsourcing techniques to predict that there might be areas that want to find out?
No, we have not, but we would be more than interested in, I mean, the more we can use the same data for, we would be more than happy to share it, really. And also, we have thought, we had once, and unfortunately the project did not come through with more characterizing and finding habitats by actually the soil characterization we're doing, and then that was for lobster in that case. Okay. Thank you.
Yeah, so following up on that,
Yeah.
the 400 or 500 drops you did in the
Right.
down to 30 to 40 centimeters, something like that, you could potentially really help us with that.
Right.
There's a lot of efforts now trying to understand where the old natural oysteries might
Right.
exist at some point. And they have died out and you want to spread it.
Yeah.
I think the data that you collect, if it penetrates far enough,
Then we
it
should see.
potentially could be relevant. You know, on your question,
Yeah.
you showed a graph with just a few data points, with some theory on it. There was one data point that really stuck out.
Right.
And I wondered if there'd been any thought to a model that suggested that.
Is this one? Yeah.
Like, it was a moisture content that exceeded a certain amount, everything looks the same. Everything greater than 7% looks the same, and then the theory
Right.
a small moisture content. Is that a potential?
So right now, Julie has implemented more data now, and now it looks as if it remains still more an outlier, and the others are
I
more.
was going to ask you, other data,
Right.
because that's just variability.
Yeah. Well, honestly, I think this is a screw up on the measurement, to be honest, and actually probably on this end. So again, we are taking the course. We're trying to be as careful as possible. But in particular, moisture content in sand and loose sands is really very sensitive. If you shake it a little bit, someone doesn't get the cap on quick enough. So that.
Is there any way to better on that? Or do you have to do a whole bunch of samples of the same thing and then get some sort of.
So we're actually trying to do that, but now we have the moisture content gauge, so we actually have two measurements of it parallel. Both of them have issues, to be honest, but so at least we have the tool to get a feel of how much are the impacts. We also optimize a little bit more sampling techniques. So our core tubes are all sharpened, they're getting inserted, we put suction on top, and then we practically dig it out, put a cap from underneath, and then lifting it out to avoid avoid that. So in one of the first data sets, perhaps not everyone was always that careful.
The idea that there is this layer of air in the foreshore area, one would imagine that slightly above this layer, you would probably see bubbles rising up, which I would expect to see spikes. You might possibly see spikes in the pressure record.
Right.
Do you see any evidence of that?
So unfortunately, we only have this one data set where it comes out that clear, in that one location where everything seemed to mesh up perfectly for that. And it was night, so we were not really out there. We saw the scour hole later, so that's why we could kind of confirm that. We did not see spikes in the pressure transducer data.
Did you see condom in the scour hole?
Yeah. Oh yeah. And that was we had a little water sitting in there. And I think that was because the water line was not. The waves got a little bit bigger than we thought, and so we were actually fairly close to the water line overnight. So there was always, from time to time, this one wave that would make it up there to refeed the pond.
You would think that it would penetrate down.
Yeah, it was really, so that's really, but that was the only concept we could really come up. And it also fits like a similar unique data set that we collected, where in fact we see on the penetrometer like this hard layer that is kind of not very deep, and you're breaking even through it, it softens up, and then we're penetrating further. And it's similar, but again, this is more of a hypothesis at this point, but we felt that it may have quite an implication of what that means for also where the run-up is being redirected in the connection of surface and groundwater in that spot.
All right, thank you, our speaker again.
Great.